good morning, afternoon, and evening to everybody on the Zoom. Thank you very much for joining us, and welcome. My name is Paul Briscoe with TAG, and I'm joined today by my TAG colleague, Peter Wharton, a name many of you may know. Hello, Peter. Say hi.
Hi, Paul. Great to be here. Thanks.
Thank you for joining us and helping us out today. And in particular, we have a very special guest today who Peter's going to introduce in a second, a very deep authority on this topic. And so we're grateful we have him with us. Just one note, we would love to answer your questions. The webinar tool provides a chat box, and we have our production staff watching that. So if you enter a question, it will go on the list, and come around the end of the webinar, we'll be happy to address the questions received. Peter, I'll throw it over to you. Please introduce our very special guest.
So I'd love to introduce you all to Pete Putman. If you have gone to the HPA Tech Retreat or the SIMTE ATC conference in LA, or at the Infocom, VIXA, or any other number of events, you will recognize Pete as an authority in the industry on displays and display technologies. And so it's really great to have you here joining us today, Pete, on this topic. Thank you.
Oh, you're welcome.
Right. So let's talk about monitors, and we're going to dive straight into monitors in a minute. And tap Pete for his knowledge. But first of all, let's talk about something historical, and the older folks, the gray hairs on the phone will know this conversation better. But, you know, we always had this thing in the industry called broadcast quality, and out of that fell something called a broadcast monitor. And these were very specific, not just because they were rack mount and very expensive. They had characteristics about them that were important to us. Today, that's not quite the case anymore. Things have changed drastically. We've moved from CRT monitors to panels. And the CRT monitors, of course, could use very special bespoke electronics to deliver the highest possible performance onto the screen, and use very high quality, high-end CRTs with very, very exacting phosphor chemistry and all of this. And today we find ourselves in a commodified world. So display panels are display panels, electronics are electronics. And the line has become gray and in fact gone away now between broadcast monitors and high-end professional panel monitors for various applications. And that leaves you in a confusing spot. What kind of monitor do you need to use for what? Your TV station. And in particular, what do you want to use for multiviewing? Because of some of the unusual concerns around multiviewing images. What makes broadcast monitors special? Well, as I mentioned, it's things like the precision colorimetry, the very tight specifications, the high tolerance, and low aging, long life electronics. Certainly the manufacturing quality was a point. The rack mountability is a thing. And what really made broadcast monitors different was the price. Many, many years ago, more than I'll tell you, I built a control room, and they wanted for the first time all the ISO monitors to not be black and white, but actually, like Program and Preview, they wanted color monitors. And we ended up buying a consumer monitor brand and putting in 100-odd ISO monitors with the pair of big broadcast Program Preview monitors. Biggest mistake ever made, because every week, 100 little monitors had to be color matched. Every week, because they were consumer color monitors. That said, fast forward to today, you walk into the TV shop, and all the pictures look the same on the wall of TVs, not like the old days where you wondered which one was the right color. So this leads us now to how do we use modern monitors effectively in broadcasting. And we're not going to talk today about things like color grading, more complicated and difficult issues. We're going to talk about the generic task of multiviewing. And so what kind of monitors and where and why do we use them? So I'd like to throw to Pete, who has deepest knowledge I've ever encountered on this topic. And he's going to talk hopefully about everything that goes on inside these things and why they're usable, what their weak points are, and what their strong points are. Pete.
Thanks, Paul. Yes, I'm largely in this field by mistake. I keep telling people that it wasn't what I planned to do, but I'm up to my neck in it now, so too late to change track. The monitor business, and in general the display business, is quite an interesting one. Back when Paul's talking in the days of building studios using CRT monitors, the CRT monitors that were used for a lot of applications were hand-built in small quantities, and you got really good prices for them. But today, your TV at home, your computer monitor, all the flat screens from your cell phone all the way up to digital signage displays are all mass-produced in large factories, mostly by robots, to the tune of hundreds of thousands of panels a month, which are made like sheets of brownies and cut up into smaller pieces to make the panel sizes that you want. So many companies have gotten into this business that the prices for a lot of these monitors has collapsed. And it's not a happy business to be in for many companies because of this cycle we call the crystal cycle, where demand drives prices up, but then by the time production can meet demand, there's too much production, demand is down, prices drop, and it goes back and forth. So right now, the dominant display technology, the Big Mac of displays, is a liquid crystal display. They're made mostly in China. There are still some factories online in Korea, at least one in Japan, and even some factories opening up in places like India and Southeast Asia. They're very easy to make in large quantities and also in very large sizes. So LCDs can be made with mother glass as large as about 11 by 9 feet, which can be cut into panels optimized for, let's say, 65 inches for consumer TVs and smaller sizes. So we can cut them any size you want. And then we also have a competing technology that's not nearly as widely adopted, and that is the organic light emitting display, or OLED. This is largely made by one company, LG Display in Korea. It is a technology originally developed by Kodak. It's a white OLED that goes through color filters to give you red, green, and blue, with an extra pixel to give you white for high dynamic range. But the vast majority of the market is still using liquid crystal displays, again, because they're not particularly difficult to make, and they can be made in all kinds of sizes, from small sizes used in monitors and cameras all the way up to 98 inch and over 100 inches that can be used for specialized applications. The thing about the LCDs is that when they first started out, you might remember their picture quality was so-so. They've gotten a lot better in terms of both color quality, and also there have been continual improvements to the backlight. An LCD panel requires light to pass through a series of light shutters. That's what liquid crystals do. They rock and twist into different alignments to pass and block light. And it's very inefficient, by the way. When you start out with a backlight, by the time the light reaches the front of the screen, you've basically absorbed 95% of it. So it's not a terribly efficient way, but it works. So we have improvements in backlight technology. We've gone away from fluorescent lights to LEDs. We've gone from LEDs to that fad where there were super thin TVs, which had all kinds of uneven backlighting. Now we're going back to what we call full array backlights. So we're able to match up backlight arrays to pixels and get a more even distribution of light. And now we're seeing some improvements in mini LEDs, small LEDs, let's say with a pitch less than 1 millimeter, to give even more density to backlights and improve things like high dynamic range and achieve higher peak luminance out of the display. But your color is always coming from color filters. And then we have some additional specialized versions of LCDs that use a technique called quantum dot enhancement, and that's an optical film or glass that's put in with these tiny microcrystalline particles that are basically zinc shells that have cadmium selenide or indium phosphide inside. And then when you hammer them with blue light, you get this quantum effect. That blue light is converted into really intense green, really intense red. So you can build a high dynamic range display using quantum dots that'll give you a peak luminance between 1,000 and 2,000 nits overall. OLEDs are not quite as capable of reaching that kind of brightness level, probably around 700 to 800 nits, but they can do high dynamic range. And they are just basically organic light emitting diodes. Inorganic ones are the ones you see for public display and everywhere from Times Square to Las Vegas to indoor displays at airports. These are organic versions of them. And they can give you really pure red, green, and blue. The problem is that the dark blue materials, have a persistent aging problem. So over time, typically about 5,000 hours or so, they can degrade at certain brightness levels to half brightness, which is one of the reasons you don't see them used in a lot of displays that are on constantly. But they can be used for everything from a multiviewer to a reference and grading monitor. Typically, in an application where you have displays on 24/7, you're probably going to want to go with an LCD.
Yeah.
Well, that's what I was gonna ask. So you said there's really OLED, quantum dot, LCD, and LED, and you're thinking that for like 24/7 LCD is the way to go.
Well, LCD is going to hold up better than OLEDs. OLEDs, because of the blue aging problem, is not something I'd recommend for 24/7 operation. But LCDs typically will last a long time. You will see some deep degradation in LCDs over time. But let's face it, they're so cheap, it's not a particularly difficult job to replace one, put another panel in, because they're comparatively inexpensive. So right now it's basically LCD and different LCD enhancements. So conventional LCD and LCD with some horsepower behind it, like quantum dots. And then we also have LCDs. So some manufacturers are just using really, really dense array of mini backlights to get high dynamic range out of it without having to use quantum dots. So that's another approach you can take. As far as the interfacing, well, they're all going to have HDMI interfaces. That's the industry standard. That's actually a consumer standard. It's not something that we would have anybody in the professional AV and broadcast world certainly would have picked as a standard, but because it's so ubiquitous, all these displays have HDMI on them. The current version of HDMI that's widely implemented is version 2, which has a maximum throughput of 18 gigabits a second. There is another version out there, HDMI 2.1, which is a purely packetized digital version with 4 lanes. However, the chipsets for those are coming out very slowly. That will have a theoretical maximum rate of 48 gigabits a second, which is really optical fiber territory. But for the time being now, we're looking at HDMI 2. And at 18 gigabits a second, that should be fast enough to do 422 10-bit 2160p or 4096 by 2160.
Hey, Pete, just a question. Why is 4 lanes not 4 times 18 gigs?
No, well, each lane is capable of, it's actually for HDMI 2, I should clarify. HDMI 2 and earlier versions use something called transition minimized differential signaling. They're not digital. They're basically same sort of thing as an extender, like a category wire extender. So TMDS has 3 lanes plus a clock. And HDMI 2.1, which is digital, has 4 lanes and the clock is embedded. It's basically HDMI's version of DisplayPort.
I didn't understand the scaling. Okay, because 48, I mean, that's right on the edge for 8K-P60.
Correct. You can do 8K 60 422 10-bit at 47.7 gigabits a second.
Right.
And my wife is right. I am a storehouse of useless knowledge. Anyway.
So Pete, I have a question for you, though. I mean, so you talked about different interfaces and such. Years ago, we worried about burn-in on monitors. Do any of these have different characteristics with burn-in when you choose a type of monitor, or are they all pretty much the same? Because I think I've seen burn-in on the backlighting as much as anything.
Well, any emissive display is going to have a burn-in problem. So anything with phosphors, OLEDs, plasma, basically you're looking directly at the source of emitted light, colored light, and those emitters over time are going to degrade. They're going to wear down. So there's really no way to get around that. So, OLEDs, the only technology right now which appears not to be impacted by that is the inorganic LED, or the more commonly the LED display. But those are capable of really, really intense, very high brightness, very high luminance colors. And right now they're not suitable for a reference display or a multiviewer because they can't get the pitch small enough. Down the road, that could change. Probably 10 years from now, you'll see micro LED monitors in the same sizes as televisions. And those will be able to easily go to $2,000 or $3,000 $10 per square meter, which is way more than you'd need for a multiviewer.
And those LEDs, are they also like the kind of panel displays they build, where they build large, contiguous monitor walls or video walls?
Correct.
Right?
Those are built out of tiles. Typically, LED displays are just like Legos. They're the Lego displays. You snap the blocks together to get what you want out of it.
But they're substantially more expensive than consumer or even digital signage displays.
Well, they are.
I mean, on the square
they
foot.
Are expensive.
Square foot,
yeah. And right now, again, given the economics of a lot of industries, including broadcasting and all, the simplest solution is the McDonald's solution, the Big Mac solution, which is LCDs, because they are available in screen sizes commercially up to 98 inches. And it's easy now with multi-viewer software to tile that, basically virtually tile that and get all the different views you want. As far as degradation goes in LCDs, it's just going to be a question of how long the LED backlights last. That's all anybody uses nowadays. And I think the jury's kind of out on that. Now, there is an image sticking issue that happens occasionally with LCDs, where you will have a image persistence in there. And that's really more of an issue in the cell. So with a multi-viewer that's focused on something static, let's say like a banner or graphics or something over time, you might actually see that if you shut the monitor off, or you may see that appear on the display at some point under another image. So there's no perfect way to get around this problem, but it's less prevalent with LCDs than it is with any type of emissive display used as a multi-viewing monitor.
So basically what it comes down to, we have these LCD displays and we use the same factory and the same functional display, whether it's digital signage or consumer. It's just really the software and the applications and maybe the interfaces for the two different ones is kind of what you were saying. What's the delta, in pricing between a digital signage version versus a consumer version of a similar sized monitor from the same company?
Boy, it's really hard to say that because the prices change constantly. The difference, I'd rather focus on the material differences.
Yeah.
If you're going to use a consumer television as a multi-viewer, which I strongly advise against, there's all kinds of gadgets and gewgaws built into it, especially in software, and enhancements, things like black stretch, dynamic gamma, auto motion plus, motion smoothing and everything. And you wind up having to turn all that stuff off because it's doing things to the image that don't look right. So you're not seeing accurate representation of gamma or contrast or motion.
Like those vivid modes and game modes and all the rest, right? Exactly.
Correct. So whereas in a what I would call, I lump these into a category. I call them digital signage monitors, but basically they're professional monitors. Mm-hmm. All of that stuff is out. Now there will be some calibration tools in there in case you want to calibrate to do specific color matching. You'll typically have a more ruggedized power supply. You may have more inputs on it. But the most important thing is that these professional monitors will generally accept a wider range of non-standard clock frequencies, pixel clock frequencies. To keep costs down in consumer televisions, everything is done with a base frequency of 74.25 megahertz, which is 720p. So 1080p is double that. Say Ultra HD at 30p is double that, and then Ultra HD at 60p is double that. So with a consumer TV, you might have one input that actually will handle non-standard clock rates, and sometimes they won't even resolve those correctly, and they'll take anything they don't understand and resort to, say, XGA or some wacky resolution that doesn't do any good. Whereas in a professional monitor, you'll be able to use some non-standard, let's say, I shouldn't say standard, they're VISA standard resolutions, but they're uncommon resolutions because they're not based on TV standard clock rates.
And one of our audience members is asking, so what's the lifespan of these different displays? What can you expect to get out of like an LCD display in a 24/7 monitor wall application, even the digital signage versions?
That is going to depend on how bright you're running the backlight. It depends on how well the display is made. It's really difficult for me to predict how long a display is going to last. And it's not really an issue that comes up anymore because, as I said earlier, the cost of these things is so low that, when they go, they're just replaced. People aren't really focusing on MTBF anymore. You might do that when you were buying a $40,000 reference studio monitor. You're not really going to worry about that if you're paying hundreds of dollars for, let's say, a 65-inch display that you're tiling to. And if it lasts you a year or two and you have to replace it, so what? It's a consumable item. And that's the point that people need to take away from this, is that displays to a lot of companies are treated the same way as things like toner and copy paper. And you buy a car and you depreciate it quickly, you expense it in a year. They're consumable items.
I guess the real downside is you really can't ever just replace just one. Odds are by the time you have to replace one, you probably want to replace them all because they don't match otherwise. They're not the same thing. They don't fit exactly. Correct. So you end up still replacing them, but it's a lot cheaper than professional ones.
Exactly.
So is there also like a difference in latency between different monitors? Between what's coming in on the HDMI or display port and what goes to the actual screen? Have you seen a difference?
Latency used to be an issue with these monitors only because of the way they address the pixels. And with some of the larger monitors a long time ago, they would start at the very top and they would write the information from the top all the way down to the bottom row of pixels, which on a small display, you'd never see any latency. First of all, you're not writing that many lines, but on a larger display, you would absolutely see it. So what the manufacturers started to do then is they would start at the top and then also halfway down, and they would be writing 2 rows of pixels at the same time. And now they can write multiple rows of pixels at the same time for almost instant refresh. So no, latency really shouldn't be a big issue anymore with these monitors.
So I'll jump in on that actually if I can, because with the consumer monitors, there is an added twist. And the added twist is all these features that consumer monitors have, like noise reduction, image enhancement, smooth motion operating, all these things. And to do these things, you need a couple of frames in memory, noise reduction in particular. So consumer monitors is actually troublesome when it comes to multiviewing, because if you turn these things on, you suddenly incur delay in the multiviewing path, and you wonder, why do I have so much latency from my video source all the way to my screen? But as well, it's more than just the latency, because these things mess with the picture in ways that multiviewing doesn't like. The one example I'll give you for, and maybe talk a little more about this later if time allows, is deinterlacing. If you have interlaced sources, we need to deinterlace these sources somehow. And anytime you deal with deinterlacing, you're doing something predictive. It's statistically, it's guaranteed not to be perfect. It's a best estimate of where the pixels go in the final deinterlaced frame. So when we display that on a normal TV, the pictures merge reasonably, and it's an organic picture, meaning it's generally a picture that has some, cohesion across itself. A multiviewer is a whole bunch of little pictures. And when you throw that at a TV set deinterlacer, that is, the output of your multiviewer is coming out interlaced, and you're throwing it at an interlaced TV, and the TV deinterlaces it. That deinterlacer is optimized for organic picture content, not for a bunch of little windows, all with their own independent motion, hard borders, and that sort of stuff. So not only do you incur the delay, which is undesirable, but you can live with, the actual artifacting caused by the panel trying to deinterlace the output of a multiviewer, which already contains, by the way, deinterlaced video sources. If you have dash I inputs to your multiviewer, you deinterlace them to multiview them. So you're deinterlacing twice with predictive processes of debatable quality, variable quality for sure, and the result is not pleasant. The same goes for enhancement. Things like spatial enhancement. You want detail, the old detail enhancement. Or in fact, color modes. That is, enhanced color, bright colors, gamma color, I call it, where one time I heard I asked somebody why their color was so high on their TV they said, I paid for a color TV and I want color, damn it. And the chroma control was full clockwise. All of these things are made to make viewers feel happy and good about their TV watching, and they're very bad for television monitoring, and they're especially bad for multiviewing. So I just wanted to say that although the panels don't have the latency, the electronics between the interface to the panel and the actual eyeball of the consumer can vary according to settings. And at the end, Peter's going to talk about how to set the monitor so that in a multi-viewing environment, you minimize latency and maximize quality by getting rid of these things. The other thing I'll just mention, weird little things in consumer monitors. Out of the box, they typically overscan. So you watch an HD picture and you're seeing 98% of it because they actually overscan the edges just in case they're dirty. And you have to go into a pixel true mode or some other funny mode to get one-to-one pixel mapping. And so consumer monitors, while they bring a great opportunity cost-wise, and performance-wise and everything, they are technically a bit of a bear, and you have to manage carefully how you set them up and so on. Sorry, Pete, back to you.
You have to specify which Pete. I would assume that if you're using
Peter.
Yeah, I would assume that if you're using multi-viewer software, though, you're outputting progressive scans to the display to begin with, and you've done all that deinterlacing and correction upstream. That's certainly the way I would do it. I would use some sort of external video processing and just feed one continuous frames of video, which have already been tiled at the correct resolution, at the correct frame rate, and also progressive scan. Then the TV doesn't really have to do anything. But in any case, you would want to shut all that stuff off if you're using a consumer TV, which, as I said earlier, I wouldn't do it in the first place. I would just use a regular monitor that's rated for 24/7 operation. And going to one thing that Peter mentioned, as far as long life, if you're in a darkened control room and you're using a multi-viewer, you don't need to have the thing running at full brightness. You can run it at a lower brightness level, which of course is going to prolong the life of the display. It doesn't need to be running. A lot of these displays now will do, I've seen some commercial displays that'll do 700, 800, even 1,000 nits. Well, you don't need that in a darkened room. You probably only need 100 to 200 maximum for a multi-viewer. So that'll also help prolong the life.
I've had a couple of people say to me, life of the display is not an issue for me because at $700 per display for my control room, I'll just replace them every year with the latest displays and I'll get better technology, and 16 people get TVs at home every year for free. So despite it not being recommended, it's the way people are going, just because they can, they can keep so many spares in the back room and they actually don't fail. I guess if you put a new one up after a year, you'd see the aging, but for commodity control rooms, people seem to be picking them. I'll give you information about the interlaced feeding the multi-viewer display. We've had a number of customers who come from an interlaced environment, so all of their sources are interlaced. And they want to re-enter their production routing system with a copy of the multi-viewer output. They want to see the mosaic as something they can punch up as a source elsewhere. Thus, it has to go back into the production system and interlace. Therefore, they want us to output interlace, which we can do. But then we say, we don't really want to do that. They say, yeah, but we have to. We have to go back into our production system for use of this elsewhere. So we're trying to, of course, steer people away from ever using interlace between the multi-viewer and the display. But sometimes people have to. So you need to at least be aware of the pitfalls.
So one thing Pete is really good at is being a prognosticator. Maybe 8 or 10 years ago, you were at the SMPTE Bits by the Bay conference and saying that by 2017, all large formats will be 4K because the manufacturers won't continue to make HD and UHD glass. It's just not worth it, or panels. So what are we going to see in the next 3 or 4 years? What's on your crystal ball?
Well, right now, that prediction did come true.
It did. It was spot on. So
because the economics are, if you're manufacturing full HD panels, you're losing money. It really is that simple.
Right.
So the new fabs that are coming on are all geared to make Ultra HD 3840 by 2160 panels. The 4096 by 2160 format is basically limited to small batch, small production LCD monitors for general applications. But if you're buying a panel now for any kind of use, multiviewer, digital signage, even the panel that goes into a TV, it's going to be Ultra HD. It's going to be 3840 by 2160. So that's an economic decision. That's not grounded in any other rational thinking. It's just that's the glass size that makes the most sense that you can make money at right now. So when you buy a new monitor, you can just assume it's going to be 4K. And if you're feeding anything into it that's not that resolution, it's going to be scaled up by circuitry within the display. How good that circuitry is, I can't say. That depends from manufacturer to manufacturer.
I can say, and it'll be terrible because it just is terrible. It's a terrible process, right?
It is, but again, in for example, commercial AV industry, which I work a lot in, the rule of thumb is if you buy a display like that, you're putting an outboard scaler ahead of it to begin with, a switcher scaler. So we're just assuming that we don't want the display to do any of the heavy lifting as far as anything to alter the image. We want to have that all upstream from it, and then the monitor just does what it's told. It just shows the pictures, and we can calibrate it to a certain white balance, color temperature, and a certain brightness level. But yes, they're all going to be Ultra HD. You've probably heard about some 8K panels. That's still a really niche specialty application. It's an expensive application. We have some companies trying to push that into the consumer space, but there's a huge premium to pay for 8K resolution at this point. And frankly, the average person is going to say, look, for 4K, which is more than enough resolution for a multiviewer, if I can get 4K and I can get it in a 75 and 85, I mean, the other day I was down at BJ's and they had 85s for under $2,000 in a consumer TV. So an 85 commercial monitor is not going to be a heck of a lot more expensive than that. So LCD is still going to rule the roost for the time being. The OLED tends to be more of a specialized application. And although LG and some other companies are pushing OLED for digital signage because of the fact that you can bend it and warp it around things, that's a bit of an exotic application, more focused towards entertainment, retail, and all. But for multi-viewers, I think LCD is going to rule the roost for a while. And the only thing that's going to replace it, and it's eventually going to replace everything, is going to be micro LED. There's too many companies working on it. There's too much money being poured into it. It works. It's expensive to make. The yields are low right now. But I have no doubt that 10 years from now, micro LED is going to be the dominant display technology, and it has the potential to push everything else out of the market.
Sure. So when is the knee on that curve? When do we see them beginning to, go down that road of becoming the next solution? 2 years, 5 years?
Oh, I think it's easy 5 years, if not a little bit more. Once we get over the knee, it's going to go up really fast. I mean, just as it did with 4K. Remember, the first 4K monitors and commercial displays were shown in 2012 at IFA. And here we are, 8 years later, and they're just ubiquitous. I mean, you can buy a 65-inch Ultra HD television with basic HDR support in it now for under $500. Those original monitors were $20,000 to $25,000 8 years ago. So we're in about a 7-year cycle. That's we seem to be for displays about every 7 years. The next thing comes along. I would say at this point, probably 2025, 2026, before you see significant penetration of micro LED.
Right. Now, meanwhile, LCD monitors have gotten entirely adequate. The view angles, the x-axis view angles are entirely adequate. The colorimetry is entirely reasonable. Of course, colorimetry is no longer even an issue. I mean, we used to have precision phosphors because there was really no way we could do LUT-based, color space conversion in the upstream of the CRT. Now your panel can be really horrible color space, and you can still use LUT conversion to get to it in a reasonable way. So, the monitors today are plenty good from what I've seen, so it's only getting better. Yeah,
we're continuing to make improvements to the viewing angle, to the backlighting, the fact that we can now do HDR, which, by the way, there are very few commercial displays available with HDR because, again, that's going all the way back to the factory. And the factory, the manufacturers are saying, well, where's the demand for that? The demand for that is consumer television. And aside from that, specialized, small batch niche operations like, post-production and all. So the vast majority of monitors that you're going to see out there for multiviewer use are going to be 709. They're not going to be 2020 monitors.
Right.
Because somebody has to show them the money. The manufacturers have to say, show me that somebody's going to buy thousands of these things a month and maybe I'll make them. But right now, if I'm only selling hundreds a month, it's not worth it to me. I can't make money on that. So the vast majority of LCD monitors are going to be 709. And we can do some things to boost the color. We can trick it up a little bit with mini LEDs and everything else to give you quasi HDR. But right now, there just isn't a lot of demand for that in the multiviewer world.
So in summary, we're saying LCD, we're looking for maybe not professional, but the digital signage versions, not the consumer television versions, but the monitor versions, to avoid all the bells and whistles of image manipulation that the consumer ones do, both because they manipulate the image, but also because that manipulation adds latency or lag in the processing. And that's really where we are at state of the art today for what we use for this monitor wall.
Correct. Yeah, you really want to use a commercial display. I say digital signage. I'm lumping them all into one category because that's basically what the manufacturers of the panels are doing. They are panels that go into displays that have a minimum of bells and whistles in them, but they have useful functions in them. And some of these displays now actually can self-calibrate. So you can, if you need to set them up for a specific gamma and a specific color gamut and a specific color temperature, the tools to do that are quite inexpensive. And in some cases, it's just one of these things where you put the sensor on the display, you attach the test pattern generator. I did this earlier this year. And it can actually connect through an Ethernet connection, and you hit start on your laptop and you leave, go out and have lunch. You come back and it's all done. So that process is relatively simple nowadays. And again, the monitors the quality control is much better on the monitors. So the stability of the calibration from one to the next is going to be a heck of a lot better than it was even 5 years ago.
Right. And then in the control, remember to turn down the brightness to make them last longer, because we usually work in darkened control rooms. And we don't need to leave them at full brightness, I guess.
Well, they'll have picture modes. They'll have picture modes built into them. So either a standard mode or, let's say, a cinema or a movie mode. That'll change the color temperature, but those will be running with most of the just about all the enhancements turned off, but something that's the most photorealistic, and that's a good point to start from.
Except some of those trick modes, they actually turn on varying degrees of some of the things, and actually it's, the pixel true everything off mode we recommend to people simply because it guarantees there's nothing going on. And then from there they can turn enhancement on.
And again, with a lot of these monitors, you can't do any calibration unless you're in certain modes, and those modes tend to be the one where everything is turned off. So there's about 10 steps you can do very quickly, even without a calibration device, to get that monitor in the ballpark. But then the calibration gets you right where you need to be. And you're really calibrating it, so making sure all your monitors match if you're doing a really wide tile display.
Right. And of course, if you ever, avoid those smart TVs, especially the ones that have the Alexa built in, because Alexa might answer questions you didn't mean for her to answer during the middle of a broadcast.
I was just going to mention that. I'll say it quietly so mine doesn't sound off. I muted it actually. But the one downside of consumer monitors that people have discovered accidentally is somebody says Alexa or something like it, and they're talking to the monitor wall. So really, there are a lot of caveats using consumer monitors, besides the quality, besides the longevity, and so on. There's lots of gotchas. So if you're using consumer monitors, I won't say don't, and I won't say at your own risk, but you need to be, like always, and like everything, be very, very aware of what you're doing. Peter and Pete, we have a couple of questions from the phone. If you'd be so kind. I think this one's probably for Pete. We're differentiating our Petes today, so Pete is.
I think we got most of the questions are already in there, but go ahead.
How many hours before an LED burns out? And it was already answered, but some additional insight might be.
LEDs, by the way, are not run continuously. Being lit by an LED light. LEDs actually can generate a tremendous amount of heat if they're run continuously. So LEDs typically are operated in what's called switched mode, or pulse width modulation mode, if you want to be more technically accurate, where they're cycled on and off very rapidly. If you If you were to take a red, green, and blue LED, say a pure RGB display, and raise the voltage on them, say from 0 to 5 volts, you'd find that the histogram looked like three drunks wandering across a parking lot, crashing into each other. So what you do is you take an LED and you bring it to full brightness, and then you cut it off. So you have a very sharp rise time, very sharp fall time. Yeah. And by doing that, you get a very pure, consistent color out of it. So to do intermediate gray steps, it's the same technique we use with digital light processing and plasma. We use pulse width modulation. So we're cycling the LED from full on to full off thousands of times a second, so fast that your eye will never see it. You can't integrate that. You can't differentiate the rise and fall times. But what happens is that you then get basically a grayscale value, a grayscale luminance value, depending on the ratio of the on-off cycles. So as far as what the lifetime of an LED is, it's really hard to say, but using PWM extends it considerably over continuous operation, because you don't have the issue with heat dissipation that you would have if you're running them in continuous mode.
Right. And last thing, and I think that's it for our questions. Just keep an eye on the chat box here. But I have a question for you guys that's my own, and I answered it myself. I'm wondering if you can figure it out. I have a large, 60-odd inch Samsung set. And recently I had dead center on the screen a bright green pixel show up. Just one pixel, and it was bright green. So anytime green was lit, I just saw only the green pixel. The red and the blue weren't visible on that pixel. And I wondered and I wondered and I wondered, and then I was able to fix the fault very easily. Can you guess what it was? And it drove me crazy. And I discovered when I looked from the side and couldn't see it lit, but from the front I could. Can you guess what happened?
Are you saying a green pixel, a tiny little dot?
Stuck pixel?
One pixel sized dot. Bright green, well, following the value of the green in that pixel's overall RGB illumination. And I fixed it from the front of the panel. I'll just tell you, it's a trick question. There was a tiny solidified dot of clear fluid in front of that pixel. I don't know if it was a sneeze that went airborne, hit the screen, but it was a lens that made only the green pixel appear when you're in front of the screen. And literally picked off this pixel-sized tiny dot of solidified clear white, clear whatever, and the problem went away. I thought, right in the middle of my panel. Cool. It was actually a little tiny lens stuck on the screen. I was
going to say, take the Sharpie and block out that pixel.
So that's how I discovered it. I had my Sharpie in hand, and I was about to go into the screen ready to do that.
Because it's stuck on is worse than it's stuck off, certainly.
So the weirdest fault in the world. So Pete, thank you for joining us today. Peter and I can talk about this stuff with some minor degree of soft authority, but to have you on this call was truly brilliant. On behalf of everyone at TAG, thank you all very much for attending. We know your time is valuable, and thank you for giving us a bit of yours today. Please ping us anytime with any questions. We're happy to help you out. In the meantime, be well, take care, and thank you.